for inviting me to participate in this wonderful program. It's wonderful to come here to the Newton Institute and to Cambridge. So I'm glad to present some recent results on coarsening rates now in the particular system of dynamics of interacting sleeping droplets. So I'm very grateful to Stephen for the first talk when he introduced many ingredients for the coarsening in general. And so I will present some particular application of these ideas to my framework, but principal difference maybe most of the talk I will work using matched asymptotic expansions, and maybe at the end I will say also some words about gradient flow structure of my model. So the physical setup of my model is very known. I think in this audience you have a liquid film on a solid substrate, say now two-dimensional liquid film, which free interface parameterized by a function h, which depends on time and position. And the main driving physical effects are surface tension of the film. Also, we consider nanoscopic films. That's why we have an intermolecular interaction of the film with a solid substrate, which are incorporated in a continuum model using this disjoint pressure, which consists of two parts. The first part is attracting van der Waals forces, and which tries to rupture the film. And when the film thickness becomes around very small, around 10 nanometers, then Born repulsion forces come into play, and they try to retract film and stabilize it around some very small profile epsilon. And the last but not least effect which we consider in our work, it's slippage. Although it looks like a local boundary condition on the solid substrate, but you see it determines globally at the end the structure of the velocity and the bulk of the fluid. And we vary slippage from zero, well-known no-slip model, to say infinity, which corresponds to the Pluk flow or suspended free films, which I will present later. So main applications.
Just a quick question.
Yeah.
Is there any role of Casimir forces here? When you go to small distances, Casimir forces.
So actually, I can't say because I didn't work with these forces. I just don't know the name of the forces, but we can maybe discuss after that. Maybe when you show me a particular formula.
I mean, the disjoining pressure can be reduced as Casimir forces of electromagnetic waves. I mean, for instance, the long-range van der Waals is derived in this way. But so some people see it as Casimir forces, some people not.
Yeah, so I would say for this moment I would just take the intermolecular pressure as it stated here and would not go to the derivation. But it's a different, very interesting topic, of course. So the basic debating of such thin films consists of several stages. As you see in this experiment, you nucleate the holes in a thin flat profile. Then they start rapidly grow, and so-called moving ridges of films forms. And then relatively quickly, these ridges form droplets, like you can see in the second experimental picture. And then in a very long time scale you see a coarsening of droplets, which consists mostly of collisions of neighboring droplets and collapse of smallest ones, where the mass is distributed through this small ultra-thin layer, order of epsilon between droplets, and gained by the bigger droplets. So you see here point from the point of view from above on a coarsening system in experiment, and you see that the coarsening happens on a very long time scale. It's around hours and days, and the natural property here is that average size of droplets increases in time and number of droplets decreases in time. And here is some numerical sketch of two coarsening mechanisms in two-dimensional case. So you see the collapse of the small droplet first, whereas its mass is distributed so due to this very small thickness layer, which is not zero but rather epsilon. And then second coarsening event, it's a collision of these two neighboring droplets when they form a bigger droplet. And so natural questions here to ask to understand physically and mathematical these coarsening mechanisms, collapse and collision of droplets, and understand at the end coarsening rates and their dependence on different physical parameters.
The morphology in the late stage there is very far from spherical. The actual droplets at this later stage.
So
Probably not done.
Yeah, I'm wondering at what stage the droplets become spherical, primarily.
So in my model, I have a linearized model. That's why I don't have a spherical equilibrium, but I have a rather parabolic
Yeah,
equilibrium.
but so
Linearized collision.
equivalently, the boundary of the droplets are not circular; they're rather deformed. So
In the experiment, you say.
yeah, it's kind of interesting. So
Yeah, so they don't have a perfect equilibrium shape, but yeah,
So I'm just wondering if this is the late stage or this is still an intermediate stage.
no, I think it's already late stage, but I cannot say why you see the equations. I mean, it depends on the experimental setting
Yeah,
which you
it's
use, of course.
Just the surface is not uniform.
Yeah. Rough.
Yeah, it's a roughness. It's in mathematics and even in theoretical physics, there is no roughness. In experiment, there is.
Yeah, absolutely. And so basic hierarchy of mathematical models could be equivalent to the hierarchy which Steven presented for his model. We should start with the Navier-Stokes equations coupled with the incompressible Navier-Stokes equations coupled with the conservation of mass. Usually due to the nano thickness of the film, you can reduce by one dimension to lubrication equations. And then, as Steven presented us, we can also reduce this infinite dimensional dynamics to finite dimensional ODE models describing coarsening dynamics of droplets. And in this talk, I would like to show you a special case which corresponds to the loop flow when beta is infinity, slip length is infinity, which can be exactly solvable, and you can derive coarsening rates analytically explicitly for this system. So the next step after you derive this reduced finite dimensional system, you're looking for the coarsening rates, and yeah. So starting with the lubrication models, which were systemized recently by this article of Milch, Wagner and Wojciechowski. They distinguished two main slip regimes. One of them is characterized by a parabolic equation for H, which is well known in this audience, so-called weak slip regime. And the second model corresponds to the strong slip regime. It's a coupled system of transport equation for H and momentum equation for U, where U is the averaged lateral velocity of the fluid. Both equations possess a conservation of mass, and both they derive from Navier-Stokes, but under different scalings of the slip length. So the demineralized parameter B, slip length, in the first model is 2 orders magnitude smaller than the demineralized parameter beta in the second model. 2 others with respect to the average physical film thickness, with which you scale your or expand your Navier-Stokes solutions. And it's shown that these 2 different scalings of the slip length results in 2 different mathematical models. In the first model, it's well known that there is a degenerate term, mobility term, and its model covers all possible mobilities and limiting cases. For example, taking B to 0 in this model, you obtain a well-known no-slip mobility H cube. And there is, okay, Also taking beta to infinity in the second model, you obtain a plug flow or suspended free films model, which was derived already by Davis and Ernois in 93, so around 20 years ago. And between these two regimes, one can find a so-called intermediate model, which corresponds to either you take b to infinity in this model and appropriately scale time in this limiting process, or take beta to 0 in this model and also appropriately scale time, and then you arrive just to intermediate slip case with mobility h squared, which is driven by the first model with mobility h squared. And sometimes
How
it's
will you get h squared here?
so I will show it so I will show how to get
It's
from this
completely
model
It is
h squared.
completely non-physical unless it is a suspended field.
I will show it on the next slide. I try to explain how to get it. So let's just make a comment. What is this? What are questions which are related to the strong slip model? So there are so-called Korteweg and visco shallow water equations, which are known already quite a lot of time, and they have a very similar structure. There is an inertial term, there is a viscous term, then shallow water equations has a curvature, linearized curvature term like for lubrication models, and there is a pressure term. So the difference with our model is that, okay, so the starting point will be if you take viscosity to constant and you take surface tension to 0, then you recover compressible Navier-Stokes equations in one dimension. And these are already very investigated 30 years ago. So another interesting case, you still have capillarity 0, but you take viscosity which depends on h, with s some power h to the power k, k between 1/2 and 3/2, for example, they consider, and you have, and they take a classical hydrodynamic pressure. So this case was considered around 5 years ago, and also if you add the capillarity terms, they called, you obtain so-called shallow water equations considered by vibration Dirigent. So our difference is that we have a different pressure term, which comes from our intermolecular interaction rather than classical hydrodynamic pressure, and we also have additional slip term, friction term minus u divided by beta.
So for the compressible gas, compressible Navier-Stokes, the H is mapped to the density.
Yes, sorry, yeah, I did. So in Korteweg case, you H is density, but in visco shallow water equations, H is.
So the crucial question in the compressible case is density positive.
Yes, and in
for
our
you,
case,
it's the same.
non-negative.
Non-negative, yeah. Super.
So maybe to explain how you can obtain also from the strong slip model this intermediate slip model, which sometimes called Navier slip model. So it's basically, it was also derived in the article of Munch, Wagner and Vitersky, that they said we rescale time with the slip length and accordingly velocity with the slip length, beta, and tend beta to 0, then you see that what remains from the system at the end, it's not so difficult to see, it's just transport equation for H, and for U you have just this equation, which exactly lubrication law for the velocity. And we just showed after that rigorously that the weak solution, so the strong slip model after this rescaling converge to the smooth solution of intermediate slip model, and that velocity weakly converge to this expression, which is exactly lubrication expression.
It's not exactly because you have only H here.
Yeah, but it corresponds exactly to Navier slip. So flux will be h squared multiplied gradient of pressure, and velocity is h multiplied by gradient of pressure. Maybe I will comment also at the end more how to understand this.
So again, is this with the momentum term included?
Sorry?
Is this theorem with the momentum term included? with the Reynolds number, so you have a fixed positive?
Inertia terms in this limiting case are, and viscosity terms disappear in this limit because they are higher order in beta, in 1 divided by beta. So they are smaller in this limiting case. They disappear, and what you recover just lubrication, a gradient of pressure multiplied by improper mobility. So what remains is the leading order. Okay, so and returning to the coarsening dynamics, as I said, after showing existence of fixed solutions, we looked at the coarsening dynamics and compared it with the coarsening dynamics known for the weak slip regime and no slip regime. And it is well known since the works of Glasner, Viteski, and Pisman and Homer that the coarsening slope is given in a weak slip model by t to the power minus 2/5. And looking at the strong slip model with Barbara Wagner, we found first interesting effect. So that the migration of droplets under the flux applied to them changes in comparison to the weak slip case. So in the later case it should migrate opposite to the flux, but we saw that taking beta sufficiently large, we can switch the migration direction of the droplet so it would migrate due to the flux. And we conjectured already 3 years ago that this should influence coarsening rates and the slope.
Wasn't there an earlier paper of Wittelski that just didn't have any, found that the I guess it's the collapse mode dominated the migration mode? Was that with no slip?
Yeah, but this corresponds to this all articles of Glasner, Otto, Viteski, Pisman. Sorry.
Right. Yeah.
Excuse me. They correspond to this weak slip model, which is just one classical lubrication equation.
Just the same coarsening rate.
And we are concentrating on the system of coupled equation for H and U and trying to reproduce the same reduction, OD reduction, and look at the coarsening rates. So starting point for any such kind of coarsening considerations is to look at the stationary solution, and it's also well known since 15 years that all lubrication models possess a special droplet stationary solutions which solves this OD and can be parameterized by the position in space. So here it's positioned at 0, and so-called pressure parameter which describes the form of the droplet. They have a well-known asymptotic, so there is a parabolic core of the droplet, and outside of the droplet there is a constant region with exactly prescribed by this parameter epsilon, and between these two main regions there is a called contact line region where a smooth transition between parabola and constant occurs, and there is good understanding of all these asymptotical regions.
So this is associated with minimizing that energy subject to a volume constraint. That's the origin of the pressure is if I take that energy that you have and I minimize subject to a volume constraint. This is the structures which come out.
Yes, exactly. It's a global minimizer of the energy with a volume constraint.
And the P is the Lagrange multiplier.
Yes, it's which corresponds to the mass constraint. So you can describe either by mass of the droplet, by radius, or by pressure. It's equivalent. And so in the weak slip regime, people show that reduced dynamics of the droplets can be, or the droplet erase, say you put as initial condition such kind of quasi-stationary solutions connected by ultra-thin layer. And they observed that each droplet can be parameterized by just two parameters, its pressure and position. And also they observed such that interaction is weak due to the fluxes between the neighbors, for example, which the droplet experience from the left and from the right neighbor. And they, by asymptotic considerations and also by gradient flow relay principle, which Steven presented us, they end up with a closed system of 2n ODs, for pressure and position evolution of droplets. So it's a coupled system of ODs, and they are coupled by the fluxes. And for the fluxes, they provided an explicit analytical formula which depends on the pressure difference between neighbors and the distance between droplets. So the dg denotes the distance between droplet g plus 1 and droplet g. So this ODE system can be effectively simulated for thousands of droplets, and from this simulation you can extract coarsening rates and check your coarsening slope minus 2/5. So I would like to present derivation by matched asymptotic analysis in the strong slip case of this system. So basically you take the full model with inertia, viscous and capillary terms and with the friction, and you just observe that in your coarsening array you also can distinguish three asymptotic regions. One is the droplet pole, where the droplet stays close to parabola, where you apply just one asymptotic expansion, and the leading order solution will be given exactly by parabola. And so this radius is related to like 1 divided by pressure of droplet, and the velocity to the leading order is 0 in the droplet core.
When you do this expansion, are you going to be keeping the Reynolds number non-zero, or?
Yeah, I can keep it non-zero, but it's comes out that inertia terms are negligible, at least until the Reynolds number becomes like 1 divided by epsilon squared, very high, which is a bit unphysical. So in all my derivation, I do not skip this term, but when I proceed asymptotic expansions, I see that it disappears if I take Reynolds number order of 1. So you can think also that this derivation valid also when you put Reynolds to 0 or to 1.
So that breaks the variational structure, but has no impact on the...
Yeah, variational structure is possible only when
has
Reynolds
no
is
impact on the leading order dynamics,
yeah.
which is interesting.
Yeah. And so in the middle region, contact line region, we should come to the moving coordinate frame, which is has a length of order epsilon, and expand again. And interestingly, we obtain that the pressure make a jump in this region, which is prescribed exactly by the flux which experienced in this region, and the velocity of the droplet and change time derivative of the pressure or radius. And if you put viscosity to 0, you see that this jump is equal to 0, and exactly what was obtained by Glasner and Vitelski for the weak slip region. They don't have a jump of pressure in this region, but as far as you have a viscous term in your model, you obtain a jump which depends in an interesting way on velocity and pressure change of the drop. And in the ultra-thin layer outside of the droplet, you have a standard expansion and standard solution that to the leading order you have a constant, and pressure solves the kind of Laplace equation in the region between droplets. And we arrive again to the closed OD system of the same form as before. Formally it has the same structure, but you should pay attention that now the fluxes have a different formula, different representation, and also mobility coefficient, which is responsible for the droplet migrations, for the droplet velocity is different and depends on the slip length beta. If you formally again put the viscosity to 0, for example, you obtain the former representation of Vitelski for the fluxes and for the mobility coefficient. So you see you obtain for this complicated model with many physical parameters a closed ODE system with explicit dependence on all physical parameters of the coefficients.
So could you just describe again this flux? It's interesting, you've got this pressure term, what the other term involves?
So it's due to...
No, it's not so much that, it's the structure in the ODE system. If you go back to the ODE system. So you've got xij dot, And then you've also got xij dot on the right hand side.
Yes, so it's another, yes, thank you very much for this question. Another difference in our models of the model of Glasner and Vitievsky, then they have a normal form, that means the dots are at the left hand side and the functions at the right hand side. Whereas we have a not normal form, because we have that our flux depends also on the velocities.
And that's
This is
the
due to this
viscosity effect.
pressure jump, which depends on the velocities and comes out in these fluxes at the end. And so you obtain a non-normal final form of the ODE in a non-normal form, and so in principle then you should, in order to obtain a normal form, you should invert some linear matrix. So
And could you just explain again the notation? So this subscript j comma j plus 1, what does that refer to?
so J refers to the droplet number J's, and flux J plus 1 is refers to the flux between droplet J and droplet J plus 1. And so numerical comparison of the full ODE system with our reduced ODE system shows coincidence of them up to the order of epsilon. So epsilon in this simulation is around 0.025, and you see that up to this order you have a very good coincidence. So you start with, say, 4 droplets, and for different slip lengths you look at the evolution either of pressures or positions of the droplet. So when slippage is 0, so this is called this limiting intermediate slip case, we know that the smallest droplet should collapse when we look at the pressures, and we see indeed its pressure blow ups in time. That means it becomes smaller and smaller and collapses. When beta is already moderate, like 5, we see that the pressure doesn't change much, but the migration increases, and mostly you see only migration of droplets and collision events. And so in this case you see that the second droplet goes, if I'm not, so the third droplet goes to the right, and the second droplet goes to the left, so they like retract each other. And so the first you see that this bigger droplet collide with the boundary droplet. Moreover, if you go to the Plug flow case beta infinity, you see that the velocities are actually constants of the droplets, and it's an interesting observation which allows us later on to reduce even more our dynamics. So in this limiting case, when beta is infinity, we know that the migration dominates completely collapse and diffusion of masses. That's why we're just looking at the leading order system for migration. And as you point out, it's not in a normal form. You have at the left hand side you have some matrix multiplied on.
It's the discrete Laplacian.
Yeah, the discrete Laplacian in this case, very simple.
But that reflects the Laplacian structure of the viscosities. It's not an accident.
Maybe I didn't think about this. But maybe. And so as I said, you somehow fix the pressures of the droplets in this process, and look just on the migration of droplets. But nevertheless, once droplet migrates, its pressure doesn't change. But when 2 droplets meet each other, of course, and form a bigger droplet, you should calculate a new pressure for the bigger droplet. And this makes troubles for the analytical consideration of such process, because it's like a jump process. You should update, at discrete times, you should update your pressures of new droplets. And this is difficult to model analytically. That's why we would like to have a system which doesn't change pressures at all and just change its positions. That's why I took a very special example, say, of initial data. And let me say, yes, okay, I took a very special example of initial data. I took a very big droplet at the right with a very small pressure P bar, and a lot of equal sized droplets with a pressure P which is bigger than P bar, but still very small. And for this initial configuration, if you see, look at this model, you see that the right-hand side is 0 everywhere, at least, but the last, so J equal N, because here is the difference between the pressures of the big droplet and small droplets come at the right-hand side. For this very special initial data, you can resolve this system explicitly and obtain a solution. And you obtain that each droplet moves with a constant velocity, as I showed, and you give an explicit formula for these velocities.
So that's periodic boundary conditions, and that big drop is coming in the other side?
No, it's not a periodic, it's no flux boundary conditions. That means you have...
so where does that big drop end?
Yeah, it's very big, so it ends somewhere here. So I just plotted.
And then there's some other, okay.
Yeah, and there are n droplets here. So just screenshot. But it's not a periodic, but no flux in this case. And so this is the explicit formula for the solution. So I write the solution in terms of the distances, not in terms of the positions. So dj is the distance between two droplets. And you have an explicit formula for so TEC, it's a collision time. You have explicit formula for the collision time, and you know how to update your distances between droplets after the collision time. N is the number of droplets. And this beta is like intensity parameter, it's proportional to the difference of the pressure of the small droplet and the big droplet, and also depends on viscosity. And so, if you know this explicit formula, you can simulate your collision events, any amount of collision events, like thousands, and construct a coarsening law in time. And interestingly, if you look more precisely on this explicit solution, you see the following. So it obeys the following rule. So more or less, once one small droplet collides with this big one, its distance dn is divided by n minus 1. It's exactly the amount of remaining droplets, and each distance of the remaining droplets obtains this amount. So that means its distance of the colliding droplets is equally redistributed between the remaining neighbors. And this observation so somehow brought me to look at these articles of physicists, which are already 20 years old, of Derrida and Bray, where they considered somehow special heuristic models for Bragg figures or Potts models, and they introduced for these models some kind of special rule of coarsening by some heuristic observations, and they derived some kinetic models from that. And so their rule is different from my rule. So they more or less it's in their case it's the evolution of fronts. Which is plus minus 1 in time. And so they constructed some kind of collision stochastic models that say they said we are given some initial distribution of the distances, like in my case between the fronts, and then we randomly or not randomly we pick up the smallest distance in our system, say this one, which has the smallest distance d minimum. And then we redistribute this distance between its two neighbors. So that means it's these two fronts collide, and the new front occurs in time, and then these two neighbors, which are staying here and here, get to their distance just a half of the colliding distance, And they, by this introducing this heuristic coarsening rule, they derived kinematic models and kinematic equation for the density evolution. And so surprisingly, I looked at this model and I saw that there is some similarity, but somehow in my case I divide this, say, smallest distance between not just two neighbors, but between all the remaining. And actually, I don't know if this model was already considered by physicists. The only things which I found is just articles of Derrida and then successors about Gizmo-Kladau dynamics. There are some generalization of this when you divide between K neighbors by some more complicated rules, but never I saw that you divide by n neighbors. So this similarity. At the end, I looked closely to the approach of Derrida and somehow reproduced somehow the explicit solution of this coarsening model in this case. If you take, say, given initial distribution of distances, that means you are given some function f0, which gives you percentage of the droplets in your array, which has a distance equal to d plus some delta d to the left neighbor. And so we are looking at the time evolution of this initial distribution. And in this case, it means you are given, you can approximate this density by taking some families, k families, such that there are, say, em droplets which has distance dm, and so the sum of all droplets as before is equal by big N. And also you order the distances in each family as decreasing, starting from 1 to the k. And additionally, to make my system completely deterministic, in contrast to what done by Derrida, they had a stochastic model. I would like to have still a more simple deterministic model. I pose my initial arrays as such that the distances are decreasing, coming from left to right. So I impose this initial distribution so that I come from the bigger distance, like 1, d1, then d2, and then 3, and then I'm coming with the smallest distant decay to the bigger droplet. For this particular initial configuration, you can, using this analytical solution, reproduce the coarsening time law, which is by iteratively applying my solution. And as I said, you would like to come to continuous limits. That means you tend n to infinity, like a thermodynamic limit, and you take some continuum initial distribution, which is after normalization is like a probability density, and you approximate it by the finite number of families. As I explained, that means you put in each interval. So if you are thinking about distribution, which is distribution of distances, and you approximate some initial distribution, you discretize your half line by delta d intervals, and accordingly you approximate your distribution by piecewise constant functions, like in a Riemann integral. That means in each interval delta d you put some finite amount of droplets, which is given by exactly by the truncation of this value. Substituting this approximation in my formula, coarsening formula, I see the clear structure that I have a leading order terms, integrals, plus some terms which are order 1 divided by n or order delta d. Delta d is my discretization of the real line. By that I can first put n to infinity and see already that I obtain clear Riemann sums in my formula. That means that when I take delta d later to infinity, I obtain a coarsening row as a perfect integral structure, which depends on the initial. So f is initial distribution. That means what's on the left hand side, you have time which is needed up to all droplets with the distances which are smaller than this d are collided by the big droplet, is given by this formula, which is just integral operator on an initial distribution. It's an explicit formula. You don't have some PD for the distribution, but you have an exactly solvable model. And if you write it in another, say, if you introduce integral of your distribution function, which is like a probability, like a relative number of droplets with the distances is larger or equal d initially, then you obtain this coarsening rate law, which you are looking usually people are usually looking at the following: how the number of droplets decreases in time. And so exactly this is the number of droplets. And this is the time which is needed to decrease all the droplets which have a smaller distance than d. And surprisingly, but maybe not so very surprising, but it looks like this time looks like relative entropy, some kind of special structure has, which I should also understand better. Maybe you know the answer for that. And to check this, so there's a formal derivation, asymptotical derivation. To check this derivation, you need just to substitute to recover the discrete formula. So this is a continuous formula, and you have initial discrete formula for array of n droplets. To recover the discrete formula, you just need to take your initial distribution as a discrete distribution. That means sum of delta functions with the weights which are given by em. And so the final question which I would like to present is what this formula tells us. What are the coarsening rates and what are the coarsening slopes? To check this, I just I was motivated at this stage already by the article of Derrida to compare my model with his model, and I just, as he took family of distributions, of initial distributions, like power law functions, and you see that they have a finite mass because alpha is bigger than 0. And what's interesting is that for alpha smaller than 1, I saw that the coarsening slope is algebraic one, so there is an algebraic coarsening rate. And if you take alpha equal 1, you obtain an exact law, which is exponential decay in droplet number in time. And when alpha is bigger than 1, it still stays as an exponential decay. So this is asymptotical formula for large times, and for alpha equal 1 is the inexact formula for all times. So that means we have a switch from the algebraic rates to exponential ones, and moreover, in the algebraic case, we cover all possible exponents more or less. Not like minus 2/5 in the classical case, but you obtain the whole bunch of slopes. But it's natural because this is more or less collision models, like governed by some kinetic equation, and there is some usually a family of self-similar solutions in this case. And to which self-similar solution you converge in time depends on your properties of your initial distribution, and exactly properties that means on decay of your initial distribution at infinity. And this decay is given by this parameter alpha. So it stays in agreement with also with the article of Derrida. For his model, he found that exactly this threshold he has at alpha equal 1/2, also switch between algebraic and exponential coarsening rates. So probably I'll show the numerical justification. So of this continuous coarsening law, this obtained by the solid line is the continuous coarsening law, and this dotted line is just a numerical simulation when you sample a discrete system, large system of n droplets, according some probability law or some initial distribution, and start to solve your ODE system iteratively and plot the coarsening time. And to compare this numerical simulation with our continuous law, we see very nice agreement for all times, except maybe the last very large times. But this is due to the sampling error, because if you sample randomly some distribution for very large n's, for very large sizes, of course you will have some error. And as I said, you have a switch between, so this is a log-log plot between algebraic decay, and after alpha equal 1 you have already in log normal plot, so that means you have exponential slope. And so interesting questions here, of course, to connect these results using some intermediate betas to the lubrication models. And there should be definitely some, if you come from infinity back to 0, you should, at 0 you have just one slope, minus 2/5. At infinity you have a very complicated dynamics. And so what's the natural question, what happens in between, how this transition occurs? Maybe falling also to Derrida approach, nice to look at the stochastic collision models in this case. This would show if this example is somehow exotic one or really in some generic behavior which is reproduced by the stochastic models. You can see similar coarsening slopes, which I saw. And as I said, I didn't say that this strong slips model is very related to viscoelastic jets, which are considered by people in the literature, so already also 20 years. So maybe returning maybe to comment to connect to the gradient flow structure which Steven presented us, as he was completely right, saying that any system can be, coarsening system can be produced by coarsening by the gradient flow structure. And I should just, and I know that many people here are interested in the gradient flow structures of physical systems. So this system also has a gradient flow structure. I do not go maybe too deep in this, but
when you drop the Reynolds term.
Yes, without inertia, of course. Without inertia, it has a nice gradient flow structure. So if you dimensionalize your models and reduce the number of physical parameters just to 2 by some scalings of time and space, you see clear two different evolution regimes. There is a so-called diffusion regime. In our case, it would call it lubrication regime. That means when your some mathematical viscosity is much smaller than mathematical slippage, then you obtain just classical intermediate slip model. So it's another justification that strong slip has as a limiting case a classical intermediate slip case. And the so-called convective or migration regime, when the viscosity is much larger than slippage, you obtain a completely different model than lubrication ones. And there are competition between viscous term now, and you cannot resolve it velocity, at least very clearly, and gradient of pressure term. And accordingly, if you look at the energy is as before, as for lubrication case, it's just surface energy plus intermolecular energy. But it has now, I don't know if you see it, two dissipation terms. So one is corresponds to classical lubrication term, which depends on proportional to gamma. And the first term is viscous term, viscous dissipation. It's similar to the dissipation in Stokes equation up to this mobility term. And these two dissipation mechanisms compete with each other. And as I said, if you go to the lubrication regime and skip viscosity, you have just classical lubrication dissipation. if you in a viscous regime, if you come to these free suspended fumes, you skip this term and you have this another dissipation. And that means your gradient flow actually is just some combination of these two dissipation mechanisms.
Maybe there's one feature for the convective regime, which is this Laplacian in the velocity, essentially. So you need another condition like the integral of u is 0.
No, I give boundary conditions for you.
But if it's periodic domain.
Yep, or non-flux boundary condition. Okay, maybe I'll stop here. Thank you very much.
Let's take a few questions.
Should we be thinking of the slip length and the sort of the disjoining pressure length scale as being related, V and epsilon?
Oh, so the good.
Well, here in this, if you want it to be physically connected, then when you have this precursor,
Right.
You don't need sleep.
Right.
Sleep already is sort of assured by this layer. So the only really physical regime here is no sleep. And for this regime, he mentioned there is in one dimension there is theory by Glassman and Vitebsky. And in the 2 dimensions, there is a paper which he didn't mention by myself and Ipo.
You mentioned it.
Yeah, I mentioned, but I didn't write. Sorry.
Okay. But then you can also notice that in one dimension, the coarsening in one dimension and in 2 dimensions is completely different. So one dimension, as Stephen really also mentioned, is an exceptional case. And
I suppose that was my other question. What's the situation in 2D? But if you answer
in 2D, yes. We have this paper, and there are simulations there because it is really ODE, so there is no. I didn't think we really came to a coarsening overall. Unfortunately, if you go to really to experiment, then the situation is still worse because all these theories are very much idealized, and so in reality everything is inhomogeneous, and then if there is evaporation actually, then this Laplace law is switched to Laplace equation, is switched to Hilbert's equation. And so everything is different. But then, after all, evaporation is an additional coarsening mechanism. And here is there are 2 coarsening mechanisms, by evaporation and by this slippage, which is by. It's not slippage, but this is a coarsening driven by disjoining pressure, because physically the precursor is thicker near the smaller droplets, and so there is such a flux within the precursor. Well, it is actually theoretically interesting questions, but nobody observed it, and you would need really a very careful experiment to see it. Well, but and regarding this strong sleep model, I don't really know whether it has any relation with anything, with any scenario.
No, I should say there are experiments by Karin Jacobs that she actually presented in Bonn with his talk. And so this was a motivation for the article for Munch, Wagner and Vitebsky. on derivation of this model. So I'm not experimentalist and I wouldn't go in details, but as I understand this, they have measured sleep in nanoscopic systems and they observe the sleep length is, can be much larger than orders larger than the thickness of the field. That's why they end up with a strong sleep model.
This has long chain polymers. So
Yeah,
the longer
but
the chains
this,
get,
this is still related. It is special for these polymers, and it's also sleep length depends, of course, on the wetting. So it may be large on non-wetting file, but then there is no precursor layer. Precursor layer, after all, can be less than a molecular thickness, and then of course the sleep lengths will dominate. But in this case, these interactions with the precursor layer would not be really, would not have to.
Well, but isn't that a circumstance where you could have an arbitrary slip length because the monomolecular layer is just changing the surface energy of the solid, of the substrate? So
Yeah,
effectively, you have a-
sleep length is practically always should be molecular molecular dimensions, but if you have big polymers then it may be larger.
Steve gets the last question.
Okay, so I was interested in trying to read off from your reduced dynamics the scaling symmetries. So what you presented at the end was developing a mean field model, an effective model from which you were deducing scaling laws. But if you look directly at these reduced dynamics, what type of scaling symmetries do they have?
I did actually. It's quite also. I didn't find scale. We didn't find so far scaling symmetries. It also depends on which equation you look, because
That's
you
right.
have
So
pressure
my
equation
point is that the origin of scaling laws is the presence of scaling symmetries. So if the scaling symmetries are not there, you can't expect universal behavior. You can't expect universal exponents.
Yeah, but there is also things that if you look at the pressure equations, like more or less like Kitavtsev successors looked, they looked at in a weak slip case, it's this equation which determines causing this mass diffusion. In this equation, to the living order, it has the scaling invariance, and this coincides with this 2 divided by fifths.
Yeah.
But now, if you look at the numerical simulation of the strong slip model, you definitely cannot say that we look just at the pressure equation. You look on both coupled equations, pressure and position, and this, I'm not sure that this coupled system has this.
So there might be a crossover effect. There might be one regime where you have scaling of one form crossing over to another, so no single scaling regime.
This could be, but this should be for moderate betas, not for the extreme cases, but for betas like not zero, not infinity.
What is beta here?
Sleep length.
Uh-huh.
So maybe for moderate beta between 0 and infinity, you can see cross.
All right, with that, let's thank both speakers.